Spinizer to because the property of components being liquid. For this, the Jeff Rau have been several important words, especially on the anthropic exchange models that can realize components being liquids. That includes a wide variety of materials and utility models, including Pyroclear system and components being ice, and also potentially also extended study and the important contribution to the study of dealing by correlates, which is very promising material to realize the complex simulations. So I think I want to take the time to look at the Rau and welcome the Rau to give a overview of the complex simulation.
All right. Thank you for that introduction. Can everybody hear me all right? Yep, I'm seeing some nodding. So, okay, so I'm going to tell you today a little bit about quantum spin liquids, and I'll try to tell you more about it at the follow-up tomorrow. This is a big topic, and so I'm only going to be able to scratch the surface. And this is also, can be a bit of a difficult topic to get your arms around. Before I prepared this talk, I went to this, perhaps you've heard of it, this AI image generation tool, DALL-E 2. You can give it a phrase, and then it spits out what it thinks that phrase looks like. And so to make this title slide, I gave it quantum spin liquid. And this is what a very sophisticated AI thinks a quantum spin liquid is, some sort of somewhat abstract oil painting. So what am I going to try to tell you about over these two lectures? I'm mainly going to try to address three questions. What is a spin liquid, and why is it interesting? I'm going to do this a little bit generally at first, but then most of this tutorial is going to be going into two, I think, sort of paradigmic examples. They're not the only examples, but I think they're two of the best examples we have, and they're also two of the examples I know best, which are quantum spin ice and the Kitaev spin liquid. And then once we've gone over those examples, I will try to come back and give you a bit of a broader picture of, once we understand what these states are and why they're interesting, we're going to try to understand how we stabilize them, for example, in real materials. How do we protect them from things like additional interactions, additional disorder, other things that show up in the real world? And then, in addition, once we've stabilized such a thing, I'll try to address the question of, well, how do we actually detect them? How do we confirm that this is what we're really seeing in a real material? And so this first one is sort of the question of, what are we studying? Why is it interesting? And next two questions are, what can go wrong? How do we actually see these things out in the real world? Okay, let's start with the definition. So what is a spin liquid? So in a very broad sense, it's a magnet that does not order down to zero temperature and is distinct from a trivial paramagnet. So let me qualify a few of these statements just a little bit. So here, when I say doesn't order, I mean does not spontaneously break any symmetries. When I say it's distinct from a trivial paramagnet, I mean it's not smoothly connected. You can't deform that state into a trivial paramagnet without encountering something sharp happening, usually a gap closing of some kind. And trivial paramagnet is being distinct from a trivial paramagnet. I just mean it has some kind of topological order, some sort of long-range entanglement in its wave function. So by this definition, something like a valence bond solid is not a spin liquid, doesn't order down to zero temperature, but it doesn't satisfy all these criteria. It is connectable to a trivial paramagnet, and typically it will actually break some of the spatial symmetries. If you have a frozen product state due to disorder, that's also not a spin liquid. Here, I'll mostly avoid the question about what this means in one dimension, just because one dimension is a little bit more complicated, mainly because we understand it a lot better. And so we have a much finer classification for these kinds of states. The systems where we find these spin liquids are typically highly frustrated and below some, and have some broad cooperative paramagnetic regime below some characteristic energy scale. Okay, so this is our definition. It's a magnet, it doesn't order, It doesn't order all the way down to T equal to 0, and it's distinct from a trivial paramagnet. So before we sort of explore that definition just a little bit, let's just be clear what we mean by some of these sort of foundational terms. So what do we mean by a magnet? So typically when I'm talking about a magnet here, I mean, I'm a theorist. So when I say what I mean by a magnet, I mean a model for a magnet. And so I mean a very general kind of spin model that might look something like this. I'll mostly restrict myself to models that have 2 states per site. So models that are spin half like or effectively spin half. But most of what I'm saying is also applicable to higher spin models as well. So anything that looks something like this, you might have some Heisenberg interactions between some spins on a lattice. You might have some additional anisotropic exchange interactions. This could include this antisymmetric Dzialushinsky-Maury interaction, or this can include the more general symmetric anisotropies. Okay, so any model of this form we'll consider a magnet. This is a little bit broader than the usual common limits people think about. A Heisenberg model where you only have this first term, XY models, where you only have exchange between 2 of the components, or an Ising model where you only have exchange between 1 of the components. Okay, so depending on what material you're talking about, what kind of atoms you're talking about, what kind of limits you're in, you can explore sort of the full range of these parameters. And in general, when you have strong spin-orbit coupling, there's no prescribed form here. Okay, so the usual expectation is if spin-orbit coupling is weak, these Heisenberg terms will be dominant. The next biggest term will be these Dzialushinsky-Maury interactions, and then the next biggest term after that will be these symmetric exchanges. Okay, but this only works when spin-orbit coupling is perturbatively small. And so once you get a little bit down the periodic table, this all goes out the window. And so you can have all of these things. So if you're talking about something like, a magnet made out of chromium or iron or cobalt, you might expect it to be somewhat isotropic. Spin-orbit coupling is relatively small here. As you go down the periodic table, ruthenium, rhenium, another row down, osmium, iridium, spin-orbit coupling goes up. You should expect a more general model. Okay, for the rare earths down here at the bottom, spin-orbit coupling is almost always complete, almost always strong. And so here you should expect these models to be completely generic. Okay, with pretty much anything involving chemistry like this, there are always exceptions. And so there are cases where cobalt spin-orbit coupling can be effectively strong. There are cases for rare earths where the spin-orbit coupling is effectively weak. Okay, so it does have to be evaluated on a case-by-case basis, but at least the general trend is we should expect that to be weak near the top of the periodic table, strong near the bottom. Okay, so that's what we mean by magnet. Let's just be a little more general here, what we mean by spin as well. When we have spin-orbit coupling, the spin and orbital of an atom are no longer distinct. And so when I say a spin model or a magnetic model, I don't just mean the spin of the electron that we're talking about. I mean some combination of spin and orbital moments, right? So for something with weak spin-orbit coupling, we might be talking about really atomic orbitals that just have spin up and spin down. But then when we add strong spin-orbit coupling, these things can mix quite strongly. And so the atomic states of interest might, instead of just being this sort of cleanly spin up state, it might be a mix of spin up and spin down that depends on the spatial position on that orbital. Okay, so all of these things will end up looking like effectively spin half models with some anisotropy, but just keep in mind, in the back of your mind, that when we're talking about these spin half states, they don't necessarily just have to be the electron spin half. Okay, so we're looking for magnets that do not order all the way down to T equal to 0 and are distinct from trivial paramagnets. Where are we going to look for this? Where do we get interesting collective behavior? So the usual route people go for here is to look for systems where you have competition between many states. Usually when you have competition between many states, that leads to complex behavior, right? And so the usual route to this is called frustration. It's when the interactions between the atoms in your system are unable to be satisfied simultaneously. Okay, so the canonical example would be a triangle where you have spins that can take one of 2 orientations, up or down, and then these things want to anti-align. These 2 here can anti-align and be happy, but there's no choice here that'll make the remaining 2 interactions between these spins satisfied, right? Up will dissatisfy this one, down will dissatisfy this one, right? So we cannot satisfy all these interactions simultaneously. There's a quote from a great Russian author that I think encapsulates this. All happy families are alike. Each unhappy family is unhappy in its own way. And the statement being, it's when there's a lot more ways to be unhappy than to be happy. And that rings true for frustration as well. So if you have an unfrustrated antiferromagnet, this is just encoding what I just said, where when they're happy when they're anti-aligned, they're unhappy when they're aligned. Then on some lattices, there's no real trouble. So if I take a square lattice here, I pick one direction for this spin. Its neighbors want to be anti-aligned. Well, I can do that easily. Fill those in with down. Now I go to the next set of neighbors. Well, they only have neighbors that are down. I can put up there. Everybody's happy. Other than that initial choice of spin, there's only one way to fill out this lattice and keep all these bonds happy, right? If we start looking at other lattices, we can run into problems, right? So if we make a lattice out of triangles, there is not any way to satisfy all these interactions at once. So if you just look at this triangle, you can find that there are actually 6 ways to make these spins equally unhappy in some sense, right? 2 of them have to be up, 2 of them have to be down, and then you get to pick where the minority spins go, right? And so you have 2 choices for whether it's minority up, minority down, and then 3 choices for where that spin goes. So there are 6 arrangements on a triangle. If I still try to fill out a lattice of triangles with spins like this, you quickly realize that there are many, many ways to do it, right? If I put an up spin here, I can fill out these surrounding triangles, keeping everything equally maximally happy, but still mostly unhappy in many different ways. And as I keep filling out the lattice, the number of choices I get to make as I go outward from this central spin does not seem to decrease, right? Here on this first triangle, I have 3 different choices I could make. Here I've got, 1 fewer. Here I've got another set I can make. And as I go out, I still find that I can keep making choices, right? No matter how many rows of this, rings of this lattice I fill out, I still have choices I can make to give sort of ground states of this lattice. Okay, and if you count these states, you'll find they actually grow exponentially in the number of spins. So this was actually worked out by Wanier, and it goes something like 1.4 to the power of the number of spins. So there's many, many of these states. And beyond there just being many, many competing states, they actually have interesting properties. So they're somewhat disordered like a paramagnet. If you just stare at this for a minute, right, it doesn't look like there's much of a pattern to these spins. But if you look at them carefully, you'll realize because of the fact that each of these triangles is in one of these 6 equally unhappy states, they're actually quite correlated. And so each triangle here actually shares one edge that is unsatisfied, right? So it's not just a paramagnet, it has these correlations built into it, right? And so this is sort of the canonical example of what's called a classical spin liquid, or sometimes called a cooperative paramagnet. So from a bit of a broader perspective, it goes something like this. We start with our frustrated magnet. This frustration leads to a highly degenerate set of states, right? Here we know nature does not like large amounts of degeneracy, especially macroscopic degeneracies. The 3rd law of thermodynamics says that's got to get lifted somehow, right? There's sort of 2 branches I've drawn here. This could go. One, you can get, you could pick out one of these states, get some kind of ordered state. This might manifest as something like order by disorder. You might get incommensurate states, interesting magnetic states, but ordered states nonetheless. Or you might resolve it by going to something a little more exotic, a little more disordered, right? So this could be something like those valence bond states I mentioned. This could be something a little more glassy, or this could be spin liquid states, quantum spin liquid states in particular, okay? So as we crank up this frustration, we're looking sort of at a picture like this. I'm drawing something like an inverse susceptibility. So as this inverse susceptibility gets lower and lower, that means it's more susceptible to, say, a field of some kind, right? And so in a typical unfrustrated magnet, you might have something like this. At high temperature, you have low susceptibility. The susceptibility increases, so the inverse susceptibility decreases. Then you have some sort of cusp or peak near a phase transition where it goes into some ordered phase. And this phase transition happens at temperatures of order the characteristic scale in this magnet, right? If you start adding frustration to the system, you can push down this scale, right? It might ultimately still order, but it might survive to a temperature that actually is quite a bit lower than what you might expect just based on the naive exchange scales in the model, okay? And so the regime we're trying to get into here is, well, can we push this scale, this ultimate transition temperature? Can frustration push this all the way down to 0? Right, get rid of that ordered phase completely. Okay. So why are these states interesting? And so this is really just sort of a top line. When we talk about the two examples, I'll show you these three features in detail for each one of them. But the top line statement here is, because these things are distinct from that trivial paramagnet, they typically come with some very unusual features. In particular, the excitations are typically fractionalized. So the sort of canonical excitations you might expect in a magnet are split into new independent parts. So as we'll see in a minute, in spin ice, you have magnetic monopoles, which are sort of like half magnetic dipole. In one-dimensional systems and spin chains, you can have spin-ons, which are like fractionalization of a magnon. This can also give rise to emergent gauge theories. So the example we'll see today is a realization of electromagnetism complete with an emergent photon. So this is what will come out when we add quantum fluctuations to classical spin ice. And the defining feature, this topological order, will shows up as long-range entangled quantum ground states, which leads to a degeneracy, which depends on the topology of the manifold on which you're putting this state. Okay. What kind of models do people usually talk about here? Well, we're looking for highly frustrated systems, right? So typically that means models that have triangles in them. So the triangular lattice was one of the first models posed for this kind of behavior. Kagame lattice is also one that's been studied in great detail in the last, I guess, 30 years now, 30, 40 years now. In 3 dimensions, we'll see this Pyroclear lattice quickly. You can see it's formed of corner-sharing tetrahedra, which themselves are made of triangles, right? So models with spin-liquid ground states. So classical models, we mentioned this triangular lattice Ising antiferromagnet. There's also continuous spin models like the Pyroclear Heisenberg antiferromagnet and other Ising models like spin ice that all have classical spin liquid ground states as t goes to 0. For quantum spin liquids, there's sort of 2 general classes here. I've sort of separated one where the model is exactly solvable. We sort of understand everything about it. The probably simplest one, but maybe just a little too esoteric, is the toric code. So this you can essentially do everything, with pen and paper, and show that it has a quantum spin liquid ground state. Kidav's honeycomb model is a little bit of a better example. You can still do everything by hand, but the model is a little more realistic. I'll talk about that in quite a bit more detail in the next lecture. And then there's a whole family of string net models which generalize these toric code models, which can realize a whole variety of different spin liquid states. A little more broadly, there's models we can't solve exactly, but through some combination of numerics or effective Hamiltonian methods or, just all sorts of theoretical trickery, we've got a good understanding of their ground states, and in particular, whether they host spin liquid states. So the Kagame antiferromagnet has been studied to death. There's still, a back and forth, on the scale of a decade, 5 to 10 years on what exactly that ground state is. But they seem to oscillate between different spin liquids rather than between spin liquids and ordered states. I'll talk today in quite a bit of detail about quantum spin ice, where while we can't solve it, it is amenable to a derivation of an effective Hamiltonian, which is then tractable using somewhat analytic techniques which have been all backed up with unbiased numerical methods. Okay, so this is one we understand quite well. There's more, for every 10 theorists, there's a model that has a spin liquid. And so there's a whole family of J1, J2 models, more exotic lattices, more exotic interactions. The list goes on. So I'm going to try to focus on these two in these lectures. So quantum spin ice today, and then Kidav's honeycomb model. You'll see that superficially, at least, they are quite different. They don't look the same, and the methods we're going to use to attack them are entirely different. But these 3 features, the fractionalized excitations, the topological order, the emergent gauge structures, will all be shared.
Question?
Yeah.
Is there a phase transition between the spin liquid and spin ice, like usual water?
between the spin liquid and spin ice. Which spin liquid?
Well,
Between
I
quantum spin
imagine
ice?
for water, you have a phase transition between liquid state and ice, right?
Right. So yeah, this is an unfortunate bit of terminology. So quantums, yeah, spin ice is a spin liquid. Yeah, it's a bit of it's just bad language, but that's just the way it goes. So the spin liquid
for
state is the spin ice state.
Okay, for a given liquid spin liquid state, if I lower the temperatures, you mentioned that it become an order state.
Yes.
Can I consider that as an ice?
You could consider that. I think the usual analogy would be if you're talking about liquids and solids, like usual structural liquids and solids, right? The solid state of the spins would be the magnetically ordered phase. So if you had something like this, where the system went from high temperature and then at some temperature ordered, you would call that something like a spin solid, if you wanted to use that analogy.
Okay, thank you.
Yeah, I'll connect to how this why it's called spin ice, and so why it relates to actual water ice a little bit later. But yes, the language is spin ice is a spin liquid. So okay, any other questions? Or I talk about quantum spin ice? No? Okay. All right, so that's sort of the overview, right? And again, it's a little broad, right? There's lots of examples and they all look quite different, right? And so I think for me at least, the only way I think I can tell you about this is to tell you about a few examples and then, cross my fingers and hope that you see some of the pattern. And so I'll start with quantum spin ice. And to go through this, so this follows this a pattern which is common for a lot of these spin liquids, but not all of them, which is you start with a classical spin liquid state, which in this case, classical spin ice, and then you perturb that with a small amount of quantum fluctuations, right? And so then you can attack this using some amount of perturbation theory to get access to this quantum spin liquid phase. So I'll tell you a little bit about this classical spin liquid and its excitations, which are magnetic monopoles. I'll talk about how you get this effective quantum Hamiltonian from perturbation theory, and then how you can analyze that to see that it really is a realization of emergent quantum electrodynamics. Okay, so what is classical spin ice? So the simplest realization of it is an Ising model on a Pyroclear lattice. So this is that Pyroclear lattice. This is a beautiful hand-drawn figure from this paper from the 1950s of Anderson, where it's one of the first discussions of this kind of model. He was thinking about charge degrees of freedom in ferrites, but the physics is quite similar. So you have tetrahedra that are corner sharing, and then these corner sharing tetrahedra fill out 3D space with their centers forming a diamond lattice. Okay. Here we're going to consider an Ising model like this. On each one of these sites of the Pyroclear lattice, we're going to consider a spin that has two different states. We'll call them up, we'll call them down, plus or minus, and that these spins are going to want to anti-align with their neighbors. So this is the simplest possible version of it you can write down. You can add additional interactions. Typically in realistic materials, you're going to want to include dipolar interactions as well. But for the essential physics, we're not going to need to talk about that. Okay. So for each one of these tetrahedra, you can see that you have the same kind of frustration you have in the triangle. You have 4 spins. They're each talking to every other spin in that tetrahedron, and they all want to anti-align, right? And so then once you anti-align 2 of them, there's no good choices for these remaining 2. There's no way to satisfy all these bonds at the same time. So this is highly frustrated. If you go and write out all the states that are, minimally unhappy, the least unhappy of the states, there are 6 of them. You can see them here. They're easily characterized by what's called the ice rule, which is that 2 of them are up and 2 of them are down. Okay, so any 2 you put here up, any 2 down, those will be ground states of this tetrahedron. 6 equally bad ways to arrange it. When I'm explaining this to you, I'm going to draw most of these pictures in 2D. Okay, so this is really, the pictures are going to be an Ising model on a checkerboard lattice, which is probably more correctly called square ice. But pretty much everything I'm going to say is going to translate over back to 3D. It'll just be a lot easier to visualize. One more small change I'll make. is instead of drawing these arrows as up and down, I'm going to rotate them 45 degrees. So instead of going up or down, they're going to go in or out of a given tetrahedron. So this is much closer to how the actual magnetic moments are aligned in the materials, but it just makes it a little, harder to draw in the other way. Okay, so this 2 up, 2 down rule in this language would be 2 in and 2 out, right? So a tetrahedron that has 2 arrows going in, 2 arrows going out will be one of your ground states. When in doubt, if you want to go back, I've colored them according to the signs of those spins. So you can go back to the colors if that's necessary. Okay, so each tetrahedron has 6 different states. You can play the same game we played for those for that triangular lattice. And you can ask, well, if I start gluing these together on a lattice, does anything change? The answer is no. So if I assign one of these 6 states to a given tetrahedron, and then I look to its neighbor, I still have more than one choice I can make here for which of the 6 states I put. I still have more than one choice here. I still have more than one choice here. And as I fill out this lattice, you see that as you keep going out and out, you keep having choices you can make, right? And so this means we end up with a ground state degeneracy, a number of these 2 in, 2 out states, which grows exponentially in the number of sites. For this square lattice case, you can actually work this out analytically. So this was something Elliott Lieb did in the 1960s. And the number of states is 4/3 to the power of 3/4 of the number of spins. Okay, and so that means that the residual entropy in this model is finite. And if you stick that into a calculator with the appropriate logs, it's about 0.2 times the number of spins. Okay, if we did this for the 3-dimensional case, you would get exactly the same answer. Or not exactly the same answer, a very exactly the same picture, which is as you filled up these tetrahedra, you would still be able to make choices as you go. You wouldn't be able to calculate this number exactly for the number of states, but the residual entropy in the 3-dimensional case is also roughly about 0.2 times the number of spins. Okay, so just like the triangular case, these are they look kind of paramagnetic. They look a little bit random. We have all these choices we can make, but they're not exactly random. They're correlated. So this can be sort of more easily seen in a kind of loop structure, which is if I take these spins and start on one spin and follow it along its arrow, what you can find is that these things always form a loop. So if, say, I start with this blue spin, I follow it to the red spin, I follow head to tail to another spin, head to tail to another spin. These things just keep going around. And if I had drawn a bigger picture here, what eventually you'd find is this thing would come around the lattice somewhere and close back up here, right? And you can do this from any spin and see a loop. So there's sort of very long correlations between these spins if you follow them this way, right? If I follow along this path, there's a relationship between a spin sort of far along this path and a spin way back here along this path. Okay. So this kind of loop structure is actually an emergent version of the usual constraint you have for magnetic field lines, which is that the divergence is 0. Okay. An easy way to see this, or sort of intuitive way to see this, is if you think of these loops of magnetic dipoles following here. I've just drawn one of them separately from the lattice here. If I lined up a whole bunch of dipoles, right, each dipole you can imagine as being a little current loop, right? And if I stacked a bunch of these current loops together, you can imagine this is like a very, long solenoid, right? If I made a loop of a solenoid, right, it carries some magnetic flux in a circle, right? Basically carries some bundle of magnetic field lines around the loop. Okay. So we're getting a sort of emergent version of the same kind of thing we see in magnetostatics, that magnetic field lines must close, they must form loops. We're seeing that in these spin configurations. One thing I want to point out, right, is that these loops are sort of everywhere, and they're not uniquely tied together. So as I follow these arrows, I don't have a unique choice of what I can do. If I follow, say, this red arrow to this blue one, to this red one, to this blue one, when I get here, I can go this way following this pink line, or I could have gone this way following this purple one, right? And so assigning these loops is not particularly unique. They're not uniquely tied together, but if you start on one spin, you can always follow, no matter which choice you make, at those non-unique points, you can always follow it all the way to the end and come back to where you started. Okay. Second statement I want to make is that because all of these ice states are degenerate, you can rearrange these loops at almost at no energy cost, right? So if I say took one assignment of these loops here, say this pink one, this purple one, right? One simple thing I can one simple change I can make to this state that doesn't violate any of these ice rules is to just permute these spins, take these two red spins, these two blue spins, and swap them, right? And so instead of having blue and then red, I have red, then blue, right? All the tetrahedra surrounding this thing are still ice states. They still have 2 in, 2 out. So that's still a perfectly good ground state. But if you look at what I've done to the loops, you can see they've changed, and they've changed in more than just this sort of trivial, which spin do I follow kind of way. You can stretch this analogy with solenoids a little bit further. So here we're saying our ground states are these 2 in, 2 out states. These 2 in, 2 out states are characterized as this tangle of loops, right? And so you might ask, well, what happens if I'm no longer in a ground state, if I'm looking at excitation, sort of in this picture of solenoids, what happens if I cut one of these solenoids, if I cut one of these loops? So in the spin picture, that might be something like taking an ice state and flipping a spin. This will be something that, like thermal fluctuations, probes like light or neutrons, they flip spins all the time, right? So this is not an unusual thing to happen, right? We flip a spin. What does that do? Well, now we're going to violate our 2 in, 2 out constraint on the 2 connected tetrahedra. So on one of them, we'll have 3 in, 1 out. On the other one, we'll have 1 out, 3 in. Okay. And so here, this thing will cost energy. It's an excitation of the system. It's no longer in the ground state manifold, right? And so I've labeled these sort of defective tetrahedra by these circles here, corresponding to whether they're 3 in, 1 out or 1 out, 3 in. Okay. Further, these sort of defects are free to move. If I flip that one spin here, generate this pair of 3 in, 1 out, 1 out, 3 in. By flipping more spins, I can actually move these defects around at no additional cost. So if I flip this spin here, what ends up happening is I move this 3 in, 1 out state over to this other tetrahedron. If I flip this one here, I move it further, and I'm not introducing any new defects. I'm just rearranging that ice state backward. Okay, so these monopoles are free to move around at no additional energy cost once they've been created as a pair. And so we can actually pull these things arbitrarily far apart for 0 energy cost. Okay. So these are the effective magnetic monopoles in spin ice. You can sort of compare this to the usual construction of a Dirac string, right? I tried to convince you, at least in a chain of analogies, that this loop structure was like a solenoid, right? And us flipping this spin is introducing sort of a cut into the solenoid, introducing an end, right? Here, these magnetic dipoles are now no longer all paired up. And so there's some collecting of magnetic flux at each end of this thing. And so in this picture, instead of having a closed loop of a solenoid, we're going to actually have some finite solenoid with open ends, right? So these open ends will be located on these defects. And just like in the usual Dirac string, these would behave effectively like magnetic monopoles. Okay, so this is sort of one of the simplest examples of fractionalization for the single spin flip. This what would be a basic excitation of an ordered magnet, that single spin flip. In this magnet, because of frustration, because of this ice background, breaks up into a pair of independent excitations, these magnetic monopoles. Okay. So it's not just theoretical. So systems exist that realize this physics. Typically, they're not in 2 dimensions. They're on this 3-dimensional Pyroclear lattice. Usually, it's the magnetic ion is some trivalent rare earth. So the family where you find these things are these Pyroclear oxides. So you have R2, M2O7. R is typically a rare earth. M is typically some sort of metal, transition metal, and then O is oxygen. So there's a huge variety of materials you can make with this family. The ones that have mostly been interest for spin ice physics are dysprosium titanate and holmium titanate. Titanium in this material is completely inert. It has nothing magnetic about it, but dysprosium and holmium are magnetic, and they sit on this Pyroclear lattice. And in fact, they end up being quite Ising. This depends a bit on the atomic physics of these materials, which I won't get into in great detail. But for example, for dysprosium, probably one of the probably the most studied example of these spin ice materials. If you go through the atomic physics for dysprosium 3+, which is the relevant valence in these compounds, what you find is that the ground state from Hund's rules has a huge amount of angular momentum. So you actually get orbital angular momentum of 5, spin of 5½ and then spin-orbit coupling joins those together into a J of 7.5, so 15 halves. Okay, so that's a giant angular momentum. Right, it's pretty much the biggest angular momentum you can get out of a single ion. Right, and this is a combination of both the spin and the orbitals from the dysprosium. Okay, crystal fields. So the effect of the surrounding ions pick out some subset of those states. Right, so here you would have 2J plus 1 subdegenerate manifold from the atomic physics, but then the spherical symmetry is broken by the surrounding ions. That splits that 2J plus 1 degeneracy, which in this case would be a 16-fold degeneracy, and breaks it up into individual levels. And so for dysprosium titanate, that crystalline electric field, mostly generated by the surrounding oxygen ions, actually prefers the states with the largest amount of angular momentum along the local z-axis. Okay, so here, this is the sort of local environment of one of these ions. It has a preferred direction, which goes in or out of these tetrahedra. And then the crystalline electric field essentially selects from this J15½ manifold the states where it's fully polarized along this direction or fully polarized against this direction. Okay, so the two states of interest are spin 1/2 state in these materials is actually the JZ plus minus 15½ states approximately. And so here, that large angular momentum comes with quite a large dipole moment as well, something like 10 Bohr magnetons. So the interactions are a bit more complicated than this toy Ising model we discussed. The strongest bit, because of those very large dipole moments, is actually the dipole-dipole interaction. So just like our toy model, where we just had this antiferromagnetic exchange, this will prefer these two in, two out configurations. So the easiest way to see this, rather than trying to do dot products, is just to imagine these things as little dumbbells of positive and negative charge, right? And so if you just put two of these spins here, right, when they're both facing this way, right, these two negative charges are in the middle. They're gonna repel. They're disfavored. When you have them going the opposite way, these two charges are attracted to each other. They're favored, right? And so in terms of these Ising variables, this is out and out. That's disfavored. Out and in. That's favored. For the Ising variables, it's antiferromagnetic. So the underlying physics is similar, but the details are quite a bit more complicated. One, dipole interactions are long range, right? They're not just nearest neighbor. They go like 1 over r cubed. Two, there's not just dipole interactions. There is also super exchange between these things. It's about half the size of the dipole interaction, so it's not insignificant. And then because these things have this very large J value, those super exchange interactions are quite complicated. At the end of the day, none of this particularly matters. The physics is not really changed by this, but just keep in mind that you can't just start with that Ising model or start with that dipolar model and just jump to the conclusion. There is some complication that has to be passed through in the middle. All of the physics that I outlined for that two-dimensional model carry through. There are many of these ice configurations, even on this three-dimensional lattice. Just like in the two-dimensional case, we can follow these loops, follow these arrows, and form some sort of soup of these loops, right? And these loops close, and then you get some emergent version of Gauss's law. And then if we flip a spin, we break our ice rule. These things have the form of magnetic monopoles. You get a pair of defects, then these defects can be separated at no energy cost. So all of that follows through. Now you're just doing it in 3D on a Pyroclear lattice rather than in 2D on this checkerboard. Just one note: why are we calling this spin ice? Right? You know, especially as pointed out before, which it is an unfortunate thing, which is that this is a spin liquid. Spin ice is a spin liquid. So the reason is this physics was first discussed, first observed in water ice itself. So here the underlying constituents are quite a bit different. Here in water ice, the oxygens are ordered, but the protons are not, right? And so the oxygens form some ordered lattice. This is hexagonal water ice. There's a whole bunch of different kinds of water ice. But once you fix where the oxygens are, you have to decide where these hydrogens go, right? And because of, you know, the residual charge on these things, you don't want two hydrogens pointing in the same direction. You want those hydrogens pointing at the oxygens, right? And so you have to try to arrange an individual hydrogen so you have the two, or the orientations of the surrounding molecules sort of avoiding each other, right? And if you write out all those configurations, you can see that basically you need to have two where the oxygen, two of these directions from the oxygen where they're pointing at the other oxygen, and then two where they're sort of further away, right, where they're not, right? And so you can map these directly to these two in and two out configurations that we've been talking about for the Ising variables. So the physics is almost identical in terms of configurations, right, in terms of that sort of simplest model, but the underlying structural constituents are quite a bit different. I will say that water ice, you know, while superficially similar to spin ice, does actually have a lot more going on in it, especially related to charge defects that are less of a problem in the magnetic version of ice. Okay, so how does this stuff show up? Well, we have many, many ground states, so we end up with this finite residual entropy, and we have these closed loops of magnetic dipoles, which basically are going to endow these spins with some sort of very long-range correlations. So the ground state should show up as some finite residual entropy as t goes to 0. These closed loops of dipoles should show up in spin correlations, and in particular should show up in static structure factor, right? Both of these things are seen in materials. We have a question?
Sorry, can I interrupt?
Yeah.
Yeah, if you consider this situation in 3 dimensions, do you need to consider the surface enclosing a monopole? Or will you create a surface that's around the monopole?
And what do you mean? Like when we're instead of
before you were considering loop, but for me, I was thinking that is because you are considered 2-dimensional setup.
Yeah, no. So yes. So you might imagine that because I went from 2D to 3D, that instead of creating a string, I'm creating some sort of membrane. But no. Yes. So in this case, I'm still creating a string, even though I'm in 3D.
And there is no surface?
There is no surface. When you pull these, basically you flip a spin, you make the pair, and to pull the pair apart, you just have to keep flipping a string of spins. So it's almost identical to the 2D case. The dimensionality doesn't really affect that.
Okay.
Okay.
Yes.
Okay. Okay. I'm running out of time. I will go faster. So the entropy is something it's difficult to directly measure, but you can get it from integrating heat capacity. You can do that. They've done that in an experiment, and they can get roughly the amount of entropy they expect. They can also see the spin correlations associated with these loops. These show up as sharp features in the Fourier transform of the spin correlations, which show up in the structure factor. Here is a simulation of that sort of simplest model, where you can see that the intensity as a function of wave vector transfer, this might be something you'd see in a neutron experiment, has this sharp feature at several points in momentum space. This is an experiment on one of these spin ice materials. You can see a similar feature, right? And so the reason this is happening is just when you go around this loop, right, which can be arbitrarily large, you're saying there's some correlation between spins that are essentially arbitrarily far apart, right? If I follow this loop, right, I'm saying these two spins are on the same loop. This sigma I and this sigma j, I'm saying something about their direction. They're correlated, right? If they're on the same loop, if this guy goes this way, this one has to go this way. It can't go the opposite way, right? So along these loops, there's correlation, right? And these loops become arbitrarily large. And so you're going to induce something long range, somewhat long range in the spin correlations. Okay. So on its own, you're going to run into problems here. Classical spin liquids are generically unstable. They're always fine-tuned. There's always something you can add to them that'll break that spin liquid state. Okay, so this is essentially the third law of thermodynamics, right? You cannot have a finite entropy density for a classical spin liquid. You need to have a finite entropy density, and so there'll always be some perturbation that will do that, right? And so the simplest scenario would be like I sketched before, which is as you come down in temperature, at some point you order, right? And that ordering temperature is determined by the scale of that perturbation, right? That's kind of the boring scenario. The more interesting scenario would be you perturb it with something. This classical spin liquid becomes unstable, but what it becomes unstable to is this quantum spin liquid, okay? And so that's what I want to talk about, and I'm now seeing with 15 minutes left, I might have to put some of that in the next lecture, but let's see how far we get. Okay, so we've constructed our classical spin liquid, which is basically just this highly degenerate ground state manifold with this extensive set of states. Okay, and so now we want to add perturbations to it, which we know will lift that degeneracy because of the third law. Okay, and the perturbations we're going to add are just general quantum mechanical exchanges, which in most materials we know have to be there, right? So this model here is a sort of generic spin 1/2 model on a Pyroclear lattice. Here is that Ising term, and then we have additional symmetry-allowed exchanges. This is a transverse exchange. This is a bond-dependent transverse exchange. This is another bond-dependent transverse exchange that, depending on the precise symmetries, the nature of the atomic orbitals, will always be there, right? It's just a question of how big they are, okay? So the question is, well, we know that this model alone has this very interesting degenerate set of states, but any small perturbation is going to destroy it. And so what do these small perturbations do? Okay. Just a small technical note, depending on exactly on the atomic states, it might be that some of these are forced to be zero by symmetry, and it might be that some of these bond-dependent exchanges, which involve these coupling constants, zeta and eta, which I have not really well defined for you here, might just be equal to 1. So that depends on some of the detailed atomic physics. If you want to read how that goes, I would recommend looking at this review article here. So for these perturbations, I will focus mainly on this bit here, sort of the simplest perturbation we can add, which is just a transverse exchange, right? So fluctuation of the spin in the direction perpendicular to this Ising direction. Adding this one gives roughly the same qualitative physics. This one is a little more complicated. Strictly speaking, we want this to be in some sense small. Otherwise, we just end up in an ordered state, okay? So with that set up, what do we want to do? Well, we have an order, an exponentially large degenerate manifold from this state here. We're adding a perturbation. So we want to do degenerate perturbation theory within that manifold. Okay. So it's a little bit unpleasant, but it's not too difficult to at least qualitatively see what should happen. So usually in degenerate perturbation theory, what you're doing, right, is you're taking an initial state in your manifold, you're applying your perturbation, right? That will generate typically a state outside of your manifold at some energy cost, right? And you keep applying your perturbation until you end up back in a state in your degenerate manifold, right? And so this can give you sort of trivial terms, constants, or this can give you non-trivial terms which connect different states from your degenerate manifold. So for this transverse exchange, the first non-trivial contribution appears actually at third order in perturbation theory. So the process looks something like this. So you take some ice state, and I've sort of grabbed some subset, some chunk of this Pyroclear lattice. Here we're sort of looking down one of these spin directions. If I take one of these states, if you look at these solid or open or filled circles, these are the satisfying the ice rules. Two are in, two are out on all these tetrahedra. If I take a bond that has two different spins, this transverse exchange has an S plus and S minus, it'll just swap them, right? It'll switch filled for open and open for filled. right? And so if I apply that perturbation, what happens? Well, I flip the spin here and I flip the spin here. So this is going to make monopoles, it's going to make defects. And so if you just stare at it for a second, you'll see you'll make a monopole here and a monopole here, right? So now we're out of the ground state manifold. The cost is of order this Ising coupling. If I keep applying this, so I apply it down here, I can move these monopoles around. So if I swap these two spins, this red one goes from here to over here, right? So still out of the manifold, still has this cost. But if I apply it one more time, I can hop this monopole all the way over to this blue one, and they'll annihilate. Okay, I end up back in a nice state. Okay, so this is the lowest order process that gives you something non-trivial in degenerate perturbation theory. Okay, so you basically create a pair of monopoles with this perturbation, a positive one and a negative one, and then using this perturbation, you hop them around the shortest possible loop, which is this hexagon, until they annihilate. Okay, and when you're done, you're in a nice state, but it's a different nice state than what you started with, right? If you stare at this carefully, right here you go white, black, white, black, white, black. Over here, it's black, white, black, white, black, white. So they've sort of flipped. So the effective Hamiltonian you get out of this, outside of these sort of trivial constant terms, is essentially just an operator that within this ice manifold just sort of flips all these spins around this shortest loop. Okay, so it takes a state where you have plus minus, plus minus, plus minus around a hexagon, and then reverses all of those spins. Okay, so as an operator, it might look something like this, where you're just flipping these things, and then you have a conjugate for when you want to flip the other way. And so this effective Hamiltonian is just going to sort of cause tunneling between ice states that have these flippable hexagons, that have hexagons that alternate like that. Because it's a third order in perturbation theory, the energy scale of this dynamics induced by this quantum term is set by the third power of the perturbation. So this is typically denoted by G here, this tunneling term. So if you work out all the coefficients, the number of different ways to do this, this is something like 12 times this transverse term cubed divided by the Ising term squared. Okay, and so I want to point out here just the hierarchy of scales. This is much, much smaller than the original perturbation itself, right? Because if the perturbation is small, then its cube is even smaller. And it's much, much smaller than the original Ising exchange. Otherwise, this perturbation theory wouldn't make sense. Okay. So we've gotten, we've taken our Ising model, we've perturbed it with this transverse exchange. Because we know that these ice states are the important states at low energy, we did degenerate perturbation theory within that manifold. We got this as our effective model. So the question is, what do you do with this? And so there's sort of two complementary approaches people have taken. One is to augment the model with an additional term, which in its phase diagram is exactly solvable. So here they've sort of schematically written the model like this, where you have this G coupling that I mentioned on the previous slide. You have a sum over all these possible hexagons that can be flipped. And then on each one of these hexagons, you have a term that just takes you from one ice state to a nice state with that hexagon flipped, and vice versa. Okay, so that model on its own is not particularly tractable. But if you add to it by hand, just stick this in by hand, instead of this tunneling type term, add a potential term for that same thing. Instead of having tunneling between a state where you flip that hexagon, you just have a term that essentially counts how many hexagons can be flipped. This model actually has a point where you can find an exact solution. So this is something that's been studied in other contexts, mainly dimer models, and it's called a Roxer-Kivelson model. And if you make these two terms equal, this potential term and this tunneling term equal, it turns out you can write down the exact ground state of this model. And the exact ground state is actually just a superposition of all the possible ice states, just complete superposition of all the degenerate all the states in the degenerate manifold. Okay. And so then the question is, if you take this exactly solvable point, which as a function of this mu is when mu is equal to G, and then you try to go back towards mu equal to 0, is that the same physics? And it turns out the answer in this case is yes, or approximately yes, where the liquid phase, or at least the somewhat spin liquid-like phase you find when these two things are equal, actually continues all the way down to mu equal to 0. Okay, so you can get some of the qualitative features of this directly from this solvable point. Okay. 5 minutes left. I'm going to have to stop somewhere. Yeah. Let me talk about this and then I will stop. Okay. So from this effective model, we can find a point that's solvable where we have something like a spin liquid ground state, and this spin liquid ground state is just a superposition of all these ice states, right? So instead of like a classical perturbation might have done, picked out one of the ice states and ordered into it, instead the tunneling term is actually picking out a superposition of all possible ice states. It's still picking out a state, but it's a much more quantum mechanical one, right? This superposition of all of this extensive manifold. One thing I want to point out is that this superposition is in fact a little bit non-unique. And so here, when we're talking about perturbing it with this tunneling term that flips these loops, we're sort of tacitly assuming that by flipping these 6-site loops, we can actually move between all the different ice states effectively, right? You know, to say that, you know, tunneling is going to cause this thing to form a superposition of all ice states, you have to assume that whatever operator is doing the tunneling can actually do that in some, you know, finite amount of time. And so it turns out, because of the structure of this ground state manifold, there's actually an impediment to this. Okay, and this can be seen by looking at the structure of these loops a little more closely. In particular, looking at the distinguishing loops that do not traverse the periodic boundaries and those that do. And so what I mean by that is here I'm drawing a loop, and this line really just means these dipoles that are head to tail like we've drawn before. I've just sort of coarse grained them a bit and just drawn them as a continuous line. So that's a loop. By flipping these hexagons, hopefully you can picture in your head that by flipping these hexagons, I can deform this loop, right? I can push the boundary out or pull the boundary in. I can deform it in some way, right? And so by applying this hexagon operator over and over again, I can deform the shape of this loop. And if I wanted to, I could shrink it. I could shrink the shape of this loop. And I could shrink it down to the smallest loop possible, right? And so by applying this hexagon flip operator, I could actually deform these loops, and I can deform one of them into any other one, right? So long as they're of some sort of finite extent. Loops that wind through the periodic direction do not have this property. They cannot be deformed into any other loop, right? So if I instead had a system with periodic boundary conditions, and so for this cylinder, imagine this bottom and this top are periodically connected, my loop doesn't have to just close up like this. It can go all the way around through this periodic direction, come back, right? And so by applying these loop flip operators, I can deform this string, but I can never get it unstuck from going through that periodic boundary condition, right? I can make it wiggle around, deform it however I want. It will still always be wound through that periodic boundary condition, okay? And so what that means is when I'm talking about this superposition of ice states, this hexagon flip move is going to have a hard time effectively connecting these things, okay? It's going to take an order, a very large number of these moves to try to actually connect these things. And so the number of loops that are winding like that actually defines a topological sector within this ground state manifold. So the only way to actually connect them is by introducing deflects. And so it's a little bit easier to see just pictorially. You make a pair of these things, plus and minus monopole pair, you pull them apart, and then I pull one of them, say this red one, through the boundary, or sorry, this blue one through the boundary, have it come back the other side, and then I annihilate them, right? So if I do that process, you can see what I should be left with is a loop that's winding through the whole system, right? If I had done that without, you know, if I just had them wander around and come back, I would just end up with a non-winding loop, okay? And so to actually modify this winding number, what you need to do is have a defect get created, have it tunnel all the way through the boundary of the system and come back and annihilate, right? So that kind of process just physically is going to be suppressed exponentially, right? And so maybe a little more physically, you should think of this as we're actually trapping magnetic flux in sort of the periodic holes of the lattice. Okay, so it looks like, am I out of time?
I think you did perfectly 1 hour talk. So I think it's time to stop and take some questions as usual. So I think you did a very clear presentation. So let's thank Professor Rau first. Okay, so I think we'll take questions. So if our online participants has questions, please also raise your hands so I can see you. So are there any questions from the audience? Okay, so students. Yeah, so maybe students can post first. Yes.
Okay. Thanks, Professor Rau. This is a very interesting talk, and I've got some experimental aspect questions.
Yeah.
So, I was told that the smoking gun evidence to demonstrate the existence of a spin gun or spin liquid is neutron scattering. But just show that there are two ways to demonstrate the spin liquid exists from the experiments. That's entropy and spin structure factor by neutron. So I'm wondering which experiments is more important, or are they equally important, or what? So the one consensus on the experimental community that's what kind of experiments when you have that data and there's no ambiguity that the spin liquid exists.
Yeah, so that's a difficult question actually. And so I'll talk, well, again, depending on the timing, hopefully I'll talk about this tomorrow a little bit. But so yes, ideally, so there's really a question of, what does it need for someone to be convinced, right? And so for something like spin ice, where is this slide? For something like classical spin ice, where we understand the model, we understand the ground state, we understand all of these things, right? Seeing the residual entropy, seeing these spin correlations might be enough to convince people that we have a good description of it, right? When we start talking about quantum spin liquids, you might say, well, we just need the same kind of thing, right? And so, one signature, the sort of smoking gun signature that people usually look for is in inelastic neutron scattering, which is evidence for a fractionalized continuum of excitations. And so this might look like the slides I didn't get to. This might look something like this, where you have wave vector and energy here. This is not experiment, this is simulation. So this is what it's supposed to look like, which is instead of having sharp quasi-particle excitations in your magnet, instead as a function of wave vector and energy, you get some broad continuum, right? And this broad continuum is representing essentially pairs of these monopoles, which because they're created in pairs, only the center of mass momentum is conserved, and so the relative momentum can change, and so you end up with a full continuum of states for each wave vector, right? And so this continuum would be sort of the standard thing people look for. In a perfectly clean and well understood system, this could be enough, right? The issue usually is there are other things that can show up as continua that aren't spin liquids. So for example, disorder can easily take something quasi-particle spectra, which should be sharp, and then broaden them out enough that they don't look that different than what you might expect for a spin liquid, right? You can also have quasi-particle excitations in certain ordered magnets that are unusually broad, right? Quasi-particle excitations at finite energy do not have to have an infinite lifetime. They can have a finite lifetime, and when they have a finite lifetime, they're broad, right? And so how broad they should be depends on the magnet, depends on the type of interaction, depends on all these things. So fractionalized continuum, I think, could be convincing, but one does have to carefully eliminate these other possibilities, namely something like disorder, quasi-particle decay, these kinds of things. Sort of the sort of best thing you could get would be some kind of actual topological response. And so in some of these Kadev spin liquids, this is what people have been claiming to have seen in thermal Hall, which is a quantized thermal Hall response. And so this is something that's hard to get from any of these other mechanisms. Unfortunately, that result in the last 5 years has not been reproduced. Every reproduction does not see the same effect. But in principle, that would be the best smoking gun for spin liquids that have that signature. For something like spin ice or quantum spin ice, what you would want, and I'll get to this next time, hopefully, would actually be to see this emergent photon that you'll end up with when we work out the connection to quantum electrodynamics.
Okay. Thanks for the answer. So are there any questions from the audience? Now, let's thank Professor Rau.